the name of God, the compassionate, the merciful, engineering plasticity, chapter 6, plastic analysis of torsion, part 3. Here is another example, which is a circular shaft with a keyway. Well, this is a particularly applied problem. As you know, circular shafts with keyways are used often in the industry, and they are usually under torsional loading as well. So this could be a very interesting problem. Now, as we said before, in order to get this function psi, we use the boundary of our cross section. Okay, the boundary here is this circular section up to here, and this circular section up to here. So if you write it down, the equations of these parts, you will get something like that times m. Okay, you have to do it yourself, this bit. And we have this equation, so we substitute for this partial derivative of psi with respect to x, second partial derivatives, and with respect to y as well, equal to minus 2g theta, and we get m equal to minus g theta divided by 2 if we use this relationship. Then x is equal to r cos theta and y is equal to r sine theta. Okay, here x and y, that is 0, that is the origin, that's x and y. So we could get x is r cos theta and r sine theta also is y, that bit. And r squared is x squared y squared, and therefore if we substitute for these in there, we get psi equal to m times r squared minus 2ar, etc. And could write Napla to the power of 2, psi equal to that. This is the transformation of the Cartesian to the polar coordinates. Okay, so that should be minus 2g theta, and m is obviously minus g theta over 2. And if we simplify this a bit, and factorize this parenthesis, we get this. So note that here is everything is constant except r and theta. And of course this theta is different from that theta. Don't forget that, okay? Maybe we should have used the different theta, different angle for this one. But this theta is different from that theta. Now, considering that psi equal to 0 on the boundary, then this should be equal to 0, and from this we get r equal to 2a cos theta. And then our shear stress to zx, and to zx is equal to partial psi to partial y, and because we have psi, we could put it in here and get this relationship. And therefore shear stress at point A to zx, so we put x equal to b. Okay, we wanted at point A, so we put x equal to b, because x starts from here. X is equal to b, and y is equal to 0, that's point A. So if we put x equal to b, y equal to 0 here, we get maximum shear stress. And that's the maximum shear stress is g theta b minus 2a. Okay, this theta I said is different. And if b becomes very small, we have just a notch on the shaft and toe max is 2g theta a. That's an interesting thing as well, because on the shafts usually we have some dents or notches or something, and they will cause stress concentrations, so that we can get the precise maximum shear stress due to the stress concentration. That's what we get. Okay, that's what we have for the keyway, and that's what we have for this. Okay, so I think that's a very interesting problem. If we have no keyway, then B is 0, and we have tau max equal to g theta a. Okay, and that's tau max for a regular circular shaft. Therefore, we could conclude that the stress concentration factor is 2 for a circular shaft that has a notch on it. But if it has a keyway, but if we have a keyway, then stress concentration would be B minus 2A divided by A. What if we want to calculate or compute the stress at point B? Okay, we could do that also. Now consider the triangle O prime B. That's O, the origin, O prime B. That's the triangle. Okay, that triangle. In this triangle, O prime B is equal to O prime, because this is a circle and these are the radius of the circle, and equal to A. Therefore, A squared is equal to A squared plus B squared minus 2AB cos alpha, because this chord here makes the angle alpha in here. And cos alpha is equal to B over 2A. And then the coordinates of point B, because we want the stress at point B. Coordinate of point B is B cos alpha B squared over 2A. And similarly, y coordinate of B is B sine alpha is B root 1 minus B squared over 4A squared. Therefore, these were the shear stress equations. So here we put for X and Y the computed value at the point B. And hence, tau Zx B becomes equal to that, and tau Zyb is equal to that. We have obtained Xb and Yb, so if we substitute for these, we get tau Zx at B becomes 0, and tau Zy at B also becomes 0. So you can see that the shear stress at B is 0. We have no shear stress at B. Now we can use this equivalent method. We have something defined as torsional stiffness. C is equal to T, which is the torque, the torsional torque, divided by theta, the torsional angle. Now for the elliptical section that we have just solved previously, we had this torque equal to that. Therefore, T divided by theta is this part. So it's that part, and A is that, and J is that for the elliptical section. So C becomes equal to that. A for J for P squared and G. So we can use this C for our computation purposes, and sometimes we use this torsional stiffness for computational purposes. Now, point matching. Point matching is also another method to obtain the torsion of prismatic bars with strange cross sections like this. Okay, that's the cross section of our prismatic bar. We have some curves like that, and the length of this curve, the chord, in fact is 2a, and the radius also is 2a, like that. The radius, this is some kind of circular section. Okay, and using psi equal to this kind of function, we could get up to the third degree. If we use, we get this kind of function, and you know, it's point matching as because this is some kind of polynomial, and therefore if you have some points here, 1 point, 2 point, 3 points, and put it there, you can fit this curve onto this equation. That's what we mean by point matching. So here, if we use this relationship, we could match the points in here onto this equation and define the curve. So this function on this curve gives us the right condition. In other words, psi is equal to 0 on the boundary, and therefore if we put this equal to 0, we get a0 equal to that, and a3 is equal to that. So these constants are obtained such that this curve matches our function, and maximum shear stress occurs at point 1, for instance, and that is partial psi to partial r, and that's equal to this, because psi is in terms of r, and we can get maximum shear stress. So sometimes we can use this kind of functions to get to the points that are interest to us, and find the shear stresses at those points. For instance, for a square section, we can use this kind of function, and in here you can see that if you consider psi is equal to 0, put this equal to 0, you can obtain a0 and a4 at these points, theta equal to 0 and theta equal to 45, like that, and then you obtain this psi by putting those constants inside it, and by changing the value of a series of sections could be obtained. Here, because apart from x and y, we have this parameter a, so if we change a, for instance, you see we get a square here like that, but if we change a along these lines, you can see that we get different kinds of squares, and you know, it rotates, and for instance, the square is here, then it goes like that. Now this is similar to a square. So you can get all sorts of shapes with these kinds of functions, and these shapes may fit onto a certain cross section. For hollow cross sections also, we can use these relations that we have obtained so far, and the way to do it is like this. This T is the torque of the hollow section that we want. Supposing this colored section is the hollow section. Okay, so this white one is hollow. There is nothing there. The material is here. So it's an annular shaft under torsion. So this T is for this color section. Okay. Now if we take X and Y like that, then we could say that TS, T of the solid section, this outside solid section, okay, supposing it's a complete solid section, that one, minus this one, TH, that hollow section, supposing it is another solid section, Okay, so if we subtract that one from that one, we get the torque for the annular shaft, okay, or hollow shaft. That's how we do it. And obviously this is for the, so far we have talked about elastic analysis. So this is clearly correct for the elastic analysis. We haven't gone into the plastic yet. So now consider an elliptical hollow section like that, okay? And then we have T is equal to this, which is for the total section, okay, for the total section, elliptical section. And this one is for the inside elliptical section with hollow elliptical section, okay? So if we subtract that from that, we get this, and this is for the annular elliptical shaft under torsion. Okay, so it's very simple. For instance, you can have a circular shaft and you can have a hollow elliptical section inside it. You can simply get the torsion of such hollow shafts.